So, welcome guys to the digital electronics basics. Today, we're going to be seeing some of the fundamental blocks for electronic circuits, that is, integrated circuits, as you can say. So, what are these fundamental building blocks? Well, these are the basic structures which can perform basic operations. So if you use n number of fundamental blocks, we can do a particular task. So that is what this basic fundamental building block. So in this case, for digital electronics, we have something called gates. So these gates made up of transistors. Transistors are nothing but switches. We are not going deep into the actual behind the picture of a transistor, but it's a simple switch. So now coming to the gates, so we have different types of gates. We have basic gates like AND, OR, and NOT, and NAND derived gates, NOT, which mean NAND and NOR, sorry. Which NOR is derived from NOT plus OR, NAND is derived from NOT plus AND, and XOR, exclusive OR, and exclusive NOR. So these are some of the gates. We'll discuss it one by one later, but first focus upon AND gate. So these are called logic gates. Forgot to mention earlier, these are called logic gates. Logic because they perform fundamental logic operations. That means if you take an AND gate, the AND gate looks something like this. So these are the inputs, A and B, called inputs, and there is an output F. Sometimes we'll say F is output, and this is the AND gate. So how AND gate works? It's just a basic logic. And if A and B both equals 1, then only our output F will be 1. Remaining all cases, its F is equal to 0. So what are the cases? First of all, we'll see, and we can comprehend all of the possibilities of A and B into a table that's called truth table. So let's see the truth table of an AND gate. It looks something like this. A, B, and output. A, B, and output F. So in a basic binary So these all gates work in a binary operations. So in binary, what are the possible values of a? Zeros and ones, right? So first of all, a 0 and b 0, a 0 b 1, and a 1 b 0, a 1 b 1. These are the all possibilities of a and b. So for a equal to 0, b equal to 0, both are 0. So for basic definition of an AND gate, from basic definition of AND gate, we can say output will be 0. And a equal to 0, b equal to 1. So here a equal to 0. So it has to be all a and b both should be 1 in order to get the output 1. So it is also 0. A is 1, b 0, that's also 0. And a1, b1, this is the case that satisfies the AND gate definition. So now the output will be the 1. This is the basic truth table of AND gate. So these gates, I already told you that these gates are made up of transistors, right? So in order to make or in order to build these gates, we use different transistors logics. Those we call logic families. So some of the logic families are transistor logic, emitter coupled logic, and CMOS logic, and so on. So these are types of logic families that we use transistor to build gates. So let's see one of the logic family here. By using CMOS logic, how we build AND gate. So CMOS means complementary metal oxide semiconductor. Metal oxide semiconductor, which is MOSFET. So we already know that what about MOSFETs, right? So here complementary means we use both NMOS and PMOS at the same time, which complement each other. The NMOS looks like this, and the PMOS looks like this, right? So by using these two, we'll build a AND gate. So AND gate will be, so let's see the CMOS implementation of an AND gate. So here in CMOS we'll be using only NMOS and PMOS. So it goes something like this. So this is the operating voltage we've been using to operate this entire design, VDD, and this is ground. This is the output, and here we will give the inputs A and B, and it will produce the output F. So this is the basic CMOS implementation of an AND gate. So you all know that in CMOS we call this a pull-up network. And this a pull down network. So we'll see later how this thing actually works in real life, for real life values of a and b and vdd later. So that's all for now. Thank you.